Okay, fine. So we'll be starting with the unit 3. So before getting into unit 3, I have to uh, tell you that this unit 3 is entirely about your fault analysis, and hence we'll be covering the different types of faults. Okay, and followed by the problems related to different types of faults. So these are the things we will be covering in this unit. And as per your syllabus, the main thing focuses on upon your Z-bus building algorithm. So you will be learning about Z-bus building algorithm in this unit, and followed by fault analysis. Okay, how to analyze your faults using your Z-bus you will be seeing, and followed by that we'll be dealing with your post-fault voltage currents and everything. Okay, so in the unit 2 we have covered entirely about your load flow. Okay, so what is the necessity of the load flow also I have just said. So to be simple, so can anybody say why we have to perform load flow? Okay, from the load flow only, the next process is about your fault analysis. Okay, from the load flow, the next step is towards your analysis of fault. Okay, so now my question is that what is the necessity of doing the load flow? Can anybody tell? So we have seen about nearly three methods, followed by the Gauss-Seidel, Newton-Raphson, and then followed by your what you can say fast decoupled methodology also you have seen. So can anybody say what was the necessity of learning load flow study? Can anybody tell me?
Sir, can you repeat the question?
Yeah, okay. So you have learned about the load flow in your unit 2, right? So what is the necessity of doing a load flow? What is the importance of doing a load flow? You have studied about load flow, and using that load flow, what we can generally do?
Sir, we can determine how much power should be supplied, sir.
Yeah, that's it. That's the main point revolving around it. Okay, you are correct. Okay, that is, for example, a network. A network might be designed for a 400 for carrying out a 400 megawatt of power. Okay, from A to B. Okay, so here it will be the generator, and here it will be your load. Okay, so this transmission line might have been, this is a simple example I am carrying out. This model might have been designed for a 400 megawatt. Okay, so using your load flow only, you can see that whether this 400 megawatt of power is carried through this transmission line. Okay, through this transmission line, whether it is carried out, we can check it out. Also, another one thing that is that you shouldn't overload this transmission line. This transmission line shouldn't be overload. Also, it should not be too much underload. Okay, the correct amount of power should be flowing from your A to B. Okay, that is done through your load flow solutions. And generally, this load flow solutions will be non-linear algebraic. So I have already dealt with it. I'll be just recalling it. It will be non-linear algebraic equation. Non-linear algebraic equations, and these non-linear algebraic equations can be solved. These can be solved. Okay, how we can solve? Through your iterative process. Through your iterative process. So through a iterative process, you will be getting the uh, optimum amount of power flow that has to be flow from A to B. So what this determines? What this determines? This determines the health of the power system. Whether the power system is in good condition or not can be determined by your this load flow solutions. These load flow solutions, it is possible to determine. Okay. From this, it is possible to determine. So this health of the power system is primarily based upon your four components. You already know that real power, reactive power, followed by voltage and your angle del. Okay, voltage angle del. So now the health of the power system revolves around the solution what we have followed. Okay, so in the normal condition, there's no problem. Okay, so your power system network will be working fine, and it will be 100% healthy. So now the problem arises. Now the problem arises when your problem arises when a sudden disturbance. Okay, when a sudden disturbance is given to your and a sudden disturbance is given to a system Okay, so this sudden disturbance is nothing but your fault. It is nothing but your fault. Okay, so for this we can take many examples. Okay, for this we can take many examples. So again, here you can see your power system. This is generator, the same thing, A and then B, and here is a static load. So this is your transmission line. So this is the system. So again, it is delivering a power of 400 megawatt. You can just have it in your mind. Okay. So now what happens? This same system, we can have an analogy. Okay, analogy means similar concept. Okay, for your understanding, I'm just explaining the similar concept. Okay, so now this is your. You can take a box. Okay, you can take a box, and what happened is that this box you can take it as D. Okay, D you can take, and over here you are applying a force. You are applying a force F. Okay, so now what happened is that this force applied over this box D, okay, will be opposed by a particular force. So this is what contributing to your moment of inertia, and which revolves around your Newton's third law, right? So this is what your Newton's third law is about. For every action, there's an equal and opposite reaction. If your force is greater than the opposing force, this object will be moving. Okay, the same thing with respect to your system also. So over the load side, you are just introducing a fault. Okay, you are introducing a fault one. What happens? This power system network, okay, this power system network will be trying to overcome this fault, and achieve the stability. Okay, and to achieve a stability, will be trying to achieve the stability condition. Okay, so for that, what happens? You have to primarily clear this fault. You have to primarily clear the fault. Okay, so the same thing is applicable over here. So the force over here is a disturbance. In order to maintain this box at equilibrium condition, you have to either apply a force which is equal to this F. Otherwise, you have to remove this entire force. So that's what to the respective to this your power system network also. The same thing revolves around your power system network also. Okay. So we will be dealing with the faults. Okay, So in order to know about the fault, you have to know about the short circuit analysis. So most commonly, okay, I'll be dealing with the types of faults. So regarding the types of faults, what are the types of faults? Means the primary thing is line to ground fault. Okay. Then line to line fault. Okay. Followed by double line to ground fault. So this is predominant in your three-phase system. So your three-phase system will be having three lines, right? With respect to that, these faults occur. So these are the different types of faults, and the most commonly occurring fault is your line to ground fault. Okay, this is the most commonly occurring fault, and this fault will be uh, of mainly due to your short circuit. Okay, this will be mainly due to your short circuit. So short circuit is the primary reason for 75% of the fault. Okay, not for a fault to occur in a system, your system might be under short circuit. Okay, so so short circuit analysis, short circuit analysis has to be performed, has to be performed before setting up of setting up of any power system. So if you're modeling a system, okay, you're going to erect a new power system. For example, you're going to erect a new power system from Chennai to, you can take Madurai. Okay, Chennai to Madurai, you're going to erect a new power system network. And this power system network, primarily what they'll be doing is they'll be modeling, and they will be doing all the load flow studies, everything. How much number of buses and how much transformers we have to erect. So the estimation and everything they will be dealing with it. And after having the model, they will be performing the load flow studies. And after performing the load flow studies, what they will be doing is they will be performing the short circuit analysis. Okay, first they will be doing with the modeling, and this modeling will be followed by a load flow, and this load flow analysis will be followed by your, what you can say, will be followed by your short circuit analysis. Since nearly, as I said, more than 75% of your power system network will be exposed to your short circuit faults. For that reason, you have to perform a short circuit analysis. Okay, so this is how the methodology involves in modeling, in erecting of a new power system network. So now we'll be dealing with the we'll be seeing various points regarding your short circuit analysis, and after that we'll be moving towards your definition of the short circuit ratio and everything. So in today's class I'll be covering just the various assumptions what we have to consider in a short circuit analysis. That's it. Okay, so you can take the heading assumptions with respect to short circuit analysis. Okay. So here the accurate fault calculations accurate fault calculations will involve much labor, okay, labor and time consumption, okay, and it will cost more time, okay, for having accurate, what you can say, accurate modeling and everything. This is applicable for all the stages. Not to have accurate modeling, not to have accurate road flow, and not to have a accurate road flow, it is possible through your computing systems. But regarding a fault and all, it is fault analysis and modeling and all, it is very difficult to get a very accurate design as well as an accurate analysis. But regarding a load flow, it is possible to get accurate value since we are having many supercomputers. So using that supercomputers, it is possible to have a very good load flow solutions. Okay, and hence what we have to do is we take some assumptions regarding your short circuit analysis. We'll be seeing what are those assumptions. Okay. First point: each synchronous machine model is represented by an EMF behind a reactance. Okay. So using this, we can determine the current immediately after the fault. Okay. So consider subtransient reactances x t dash. So what they are saying is that while before performing the short circuit analysis, they had to consider an assumption, not to have an approximate analysis. Okay, so the thing is that you have to consider a reactance value after the generator or your synchronous machine, that mainly after your generator. So why it is used means I'll be explaining. If I am showing the diagram, it will be easy for you. So this is how it looks like. So this way you can consider as your EG or your EB. So this represents your back EMF. So generally in your synchronous machines, mainly your AC machines, there exists back EMF. And what they are asking to consider is that the first assumption is that you have to consider a XD or a reactance value. So why it is necessary to consider this subtransient reactance means this represents your subtransient reactance. Why you have to consider this XD dash means there might be a sudden amount of current flow. Okay, there might be a sudden amount of current flow over this network. Okay, if this is absent, if this is not present, means it becomes a very tedious process to measure that current. Okay, it becomes a tedious process to measure that current. So our ultimate aim is to measure the current caused by the fault. Whenever the short circuit occurs, you already know that the current flow increases heavily. Okay, so not to measure such kind of current, you have to add a subtransient reactance. But this subtransient react, you might be asking, so if you're adding a reactance, means whether it affects the model or if it affects the nature of the system, you might be asking. The thing is that the subtransient reactance, what you are adding, will be of a very small value. The value of this subtransient reactance will be very small. So it will be very easy for you to find the current flowing through this reactance. Okay. And then moving on to the second assumption. In transformer model, shunt elements that account for magnetizing current, comma, core losses are neglected. So generally, what they're saying is that in the transformer, you have to neglect your loss. That to mainly your core loss. So why this occurs means, again this is with respect to your current. Okay. So whenever the current flows high in the what you can say uh, in your transformer, you know about the transformer equivalent circuit. You will be having a, core. Okay, you'll be having a, like this in the equivalent circuit you'll be having. So you'll be having your R followed by the X naught. Okay. So the magnetizing current will be flowing, as well as the core current will also be flowing. So what they are saying is you have to neglect this magnetizing losses in case of your transformer. So this is another one assumption. Okay. So if you are just using this assumption, it might be possible to get a very good short circuit analysis. The third point is, in the transmission line, shunt capacitance are neglected. You have to neglect your shunt capacitance. Okay. And the fourth one is, all series resistance in generator, comma, transmission line, and transformers are neglected. Okay, so the basic principle behind these kind of assumptions is that they will be neglecting most of the passive components. Okay, they will be neglecting most of the passive components in the electrical equipments like transmission line, transformers, generators, and everything. So why they are neglecting like that? The basic principle of neglecting and taking these assumptions, I'll be telling while calculating, while doing your short circuit analysis. Then it will be easy for you to understand. So the fifth one is, you have to consider the flat voltage profile. So you know about flat voltage profile. I have already taken. So in normal operating conditions, bus voltages of a power system network. Are usually kept close to their close to nominal value. Okay. And, the pre-fault voltages in the network and including the pre-fault voltage at fault point can be taken as flat voltage. So, cutting this, what they are saying is that if you're considering a point, okay, for example, you consider A to B, okay, the same example what you have seen. You consider this A to B, and from this A to B, you have to perform a short circuit analysis, okay. So at that time, you have to consider your pre-fault voltages. For example, if this B is of 0.08, sorry, 0.8 per unit in the sense, uh, before introducing this fault, you have to consider the voltage in this bus to be as a flat voltage profile, that is 1 per unit. Okay, that is 1 per unit. This is one of the assumption. Before introducing the fault, the corresponding bus, the fault which is occurring to the nearby bus, you have to consider the voltage of that particular bus to be as per flat voltage profile. That is 1 per unit at an angle of 0 degree. Okay. So
Sir,
coming to the sixth assumption.
in this manner, what you are saying, are we introducing the faults or the faults which are natural occurring, sir? Because you are saying like,
Yeah, that what I'm saying is that so in this process will be these process and all done by the power system engineers before setting up a power system network. Okay, so what happens is that they will be doing a pre-fault analysis also. So in this itself, there will be in the fault analysis itself there will be two types. One is your post fault and then followed by a pre fault. Okay, that is how your system will be performing before the fault and after the fault. Like that, the power system engineers will be analyzing. So during that condition, I'm just saying. Okay. So you just don't get confused that whether it is happening in naturally or those things and all. You just don't think before setting up of a power system. These analysis and all performed entirely by the power system engineers. So that's what we are considering now. Okay. So the sixth point is that the load impedances are neglected and therefore the pre-fault system is unloaded. Okay. So why we are doing this means Why we are doing this means during short circuit, huge amount of current okay. So during short circuit fault, you know that excess amount of current will be flowing, and hence you have to neglect your load impedances. So if you're neglecting your load impedance means most of the period, as per these conditions, your load will be in the unloaded condition. Okay. These are some of the assumptions, and the final assumption is that your pre-fault current are much smaller than your fault current. So this you already know. And hence the pre-fault current can be neglected. Okay. But for post fault current calculations, okay, the pre-fault current has to be considered. So these are the assumptions regarding your short circuit analysis. Okay, so we just go through these 7 points, and based upon these 7 points, we will be performing the short circuit analysis. And before getting into the short circuit analysis, we will be learning about how to build the Z bus, because your entire short circuit analysis or the fault analysis revolves around your Z bus building algorithm. So we'll be seeing about your Z bus building algorithm in the next class, and some problems we'll be considering. And after that, we'll be getting into your short circuit analysis. Okay. So if you are going to build the Z bus, okay. So we have in the load flow analysis, we have seen how to build your Y bus or your admittance matrix. Okay. Uh, so during that case, I just told that Z bus will be dealing with your when you are seeing your short circuit analysis. The Z bus will be covering in this unit that in the next lecture will be seen. Okay. So that's what with respect to today's lecture. So load flow, I'll be putting out the recorded session, and Postnet also will be putting out, because the same as set of your Newton interaction, you can just see through it. Okay. So this you can complete today's session. Thank you. And I think Srihari is there, right? Srihari?
Sir,
Srihari, can you send me the previous lecture recorded video?
okay, sir. I will send to your mail ID, sir.
Okay, Srihari. Thank you. Thank you, Srihari.